It's a pleasure to be here. I think this is an overdue visit to Stanford, probably. I haven't been here for a long time, even though Sebastian had been inviting me for a long time. But I'll talk about memory system design, and hopefully I'll give you some hope that we still have hope in this domain. But before I start, very quickly, what do I work on? Well, clearly I work on memory, storage, and interconnects, but I'm really interested in computer architecture, hardware-software interface, and also bioinformatics. These are some of the things that my group looks at: parallel architectures, heterogeneous architectures, GPUs. We have big projects related to that. I'm really interested in crossing the boundaries, and hopefully you'll see themes of that in this talk: system architecture boundary, as well as the architecture circuits boundary. And going forward, especially if you want to design more scalable memory systems, I think we need to cross those boundaries even more than we have done in the past. So you'll see themes of energy efficiency, fault tolerance, and hardware security in this talk. But basically, I like doing broad research spanning applications, systems, and logic with architecture at the center. And this is kind of the little picture I have related to the research. And one of my interests is genome sequence analysis and assembly. And this is a problem where it's really, that motivates memory a lot. I look at algorithms in this area, but it's an area, it's a big data area where we produce more data than we can process today, actually, with the next generation sequencing technologies, which are actually current generation. But I'll talk about memory in this talk. And what are we talking about? Basically, main memory sits in between processor and caches and the storage. And it's a critical component in all computing systems we design. Basically, we need to have some kind of working storage, as Andy mentioned earlier. And this system must scale in many, many dimensions: size, technology, efficiency, cost, and the algorithms we use to manage it if you want to maintain the performance growth and the technology scaling benefits. And this is another view of the memory system. This is my cartoonish picture of it. But there are two key points that I would like to make over here. One is, if you look at the computation components in this cartoonish picture, they're limited to the red parts. Basically, everything else is part of the memory system. Basically, we're designing these nodes, systems, and most of it is really dedicated to moving and storing data. And even if you look at the red parts internally, a lot of it is dedicated to moving and storing data. We have the registers and interconnected L1 caches that I didn't paint. And the second thing is, if you look at this, most of the memory system is shared across these computational agents. Shared caches, other shared caches, shared memory controllers, shared memory, shared interconnects. And that leads to quality of service problems. I'll briefly talk about that today. Let me tell you a little bit about the state of the main memory system as I see it today. There are some recent technology, architecture, and application trends that lead to some new requirements from the system, and that also exacerbate some old requirements. And we've always demanded a lot from the system, and we're demanding even more. I'll posit that DRAM and memory controllers, as we know them and as we design them today, are unlikely, or they are not able to satisfy all of these requirements. And I'll hopefully give you some evidence from the field based on some of the studies we've done. And at the same time, there are some emerging memory technologies that happen to be non-volatile that enable some new opportunities, like the merging of memory and storage. So hopefully we'll get to the end of the talk where I will talk about that. Given these, I believe we need to rethink the entire main memory system and the system we design around it, or the systems we design around it, to fix the issues we're having with DRAM and enable some of these emerging memory technologies while satisfying all of the requirements that we demand from it. So this is an outline of my talk. This could be a really long talk. This could be days and days, but I'm going to compress it to 1 hour, 8 minutes remaining. Feel free to ask questions. I may need to limit it, given that we have a time limitation. But I'd be happy to have a discussion afterwards or some other time as well. Feel free to email me. But I'll talk about the major trends affecting main memory. And then I'll pose everything as a memory scaling problem and talk about two major solution directions: looking at new memory architectures and enabling emerging memory technologies. And circle back and talk about how we can do better, draw some principles, hopefully. Hopefully none of this will be surprising principles, because a lot of them will be applied from some other domains. And then I'll summarize. This is in one slide the major trends that are affecting main memory as I see them. First, we're demanding more memory bandwidth, capacity, and quality of service. And this is really driven by three major things. We're putting increasingly more computational agents on the chip. They're sharing the bandwidth, they're sharing the capacity, they're sharing the resources. As a result, you have a predictability problem. Applications are becoming increasingly data intensive. And this is not going to change. Probably we're at the point in civilization today we're generating the most data, and we're going to generate even more, in my opinion. And we want to consolidate more and more. Regardless of whatever system you design, cell phone, data center,
We would like to put more applications running on the node such that we can get area, cost, and energy efficiency benefits. And this is driving the capacity, bandwidth, and quality of service requirements up. This is just one example, the capacity gap. This is actually from a paper that was published by HP Labs at the University of Michigan in ISCA 2009. Basically, they plotted the core count, which is doubling approximately every 2 years. They plotted the DRAM DIMM capacity, which is doubling approximately every 3 years. And they've shown that memory capacity per core is expected to drop by 30% every 2 years. Now, if the program is relying on a thread getting more memory such that you can write more featureful software, then that's not going to happen, assuming you're utilizing your resources well. And the trends are actually much worse for memory bandwidth per core. Memory bandwidth grows by approximately 10% every year, with some bumps maybe. But basically, we're designing these systems where computation is increasing, growing much faster than we can provide capacity and bandwidth. Basically, we're starving the cores. The second major system trend in memory is energy and power is a key system design concern. And this has been like that for a while, except it's getting much worse today. There's a really nice paper by Charles Lafergie and others at IBM Research where they published real data from big iron systems of IBM in 2003. And they've shown that approximately 40 to 50% of the entire system energy in this big iron systems is spent on the off-chip memory hierarchy, including the off-chip interconnect, off-chip caches, off-chip DRAM, and off-chip storage. And that's a big fraction. And other people have repeated the studies on mobile systems. And one issue we're having with DRAM is it consumes power even when it's not used. We basically need to periodically refresh it. And that's actually a big scaling problem of DRAM today, which brings me to my third point. DRAM technology scaling is ending. And if ending is a strong word, you can choose the other word, which is becoming really difficult to deal with. But ITRS, International Technology Roadmap of Semiconductors, has been projecting for a while that DRAM will not easily scale below X nanometers. Anybody has a value to assign to X? 3. Wow, that's very optimistic. Maybe, yeah, we'll see. It may become 3, but definitely driving that X down will be increasingly more difficult for us. And I'll hopefully give you some evidence from the field that we're actually seeing the scaling issues, feeling the scaling issues. But scaling, what do I mean by scaling? Basically, you reduce the size of the circuit, and that provides you many benefits: higher capacity, higher density, lower cost, and hopefully reasonable energy scaling. And if this ends, we're not going to be able to satisfy these requirements really well, at least with the technology the way we have known it. So let me pose everything as a memory scaling problem and motivate you a little bit more, and then talk about some solution directions. So what is the scaling problem we see with DRAM? Basically, DRAM, like any other memory, has a storage device and an access device. And the storage device in DRAM is a capacitor. Access device is the access transistor, the bit line, and the sense amplifier over here. And for this to work well, the capacitor must be large enough for reliable sensing, and this access transistor must be large enough for low leakage and high retention time, such that you keep the charge over here. And this was actually the value that was assigned to X by ITRS in 2009. Basically, they said scaling below 35 nanometers is challenging. And they were actually right, in my opinion, because of what I'll describe next. Except we're clearly below 35 nanometers today. DRAM manufacturers are actually manufacturing chips at 20 nanometers and below. But it's clear that it's challenging. When you reduce the size of the circuit, both of these properties, reliability properties and the retention properties, become much more difficult to maintain. So let me give you an example from the field that my students and I have found out and reported in this ISCA paper. And the idea is, this is a row hammer problem. Basically, if you take a DRAM chip that's manufactured after 2010, maybe before 2015, and if you actually do what I'm going to describe to that chip, you'll get errors in the chip. And the idea is you can activate a row, open a row, and then by applying high voltage to the word line, and then you can close the row by pre-charging that word line, basically go back to the lower voltage. And if you keep doing this enough times, toggling the word line enough times within a refresh interval, you get errors in adjacent rows. Now, this is called the row hammer problem, and this is actually a disturbance error, basically. It's a very fundamental to any type of memory that scales down to smaller nodes. You're basically, by applying high voltage over here, you're accelerating the charge leakage on some of the weak cells that are due to the word line to word line coupling that are in the adjacent row, but that have nothing to do with this row over here. And we call this the hammered row, and we call these the victim rows. And basically, we've shown that you can this is a failure mechanism that have escaped and that you can get exposed as a user in the field if you have the DRAM chips. And what fraction of the DRAM chips are vulnerable? Among the ones we've tested from 3 different manufacturers, more than 80% exhibit this error. And you can actually write a simple program, a 7-line user-level program, which we published at GitHub, so you can download it and you can test on your laptops as we go through this talk. What this program does is it exercises that by bypassing the caches and selecting addresses X and Y such that they map to the same bank, and basically ping-ponging the activates and precharges across those. As a result, if you have a vulnerable chip, you get some errors. And you can, by using this program, you can actually see that existing systems are vulnerable if they have the DRAM chip that exhibits this failure mechanism. And a more controlled, it's a real reliability and security issue, and we'll talk about why it's a security issue in a little bit. But in a more controlled environment, you can actually induce a lot more errors than what we've seen over here. And clearly, the errors correlate with the access rate, because you need to do it enough times such that you extract the charge leakage and drain the capacitor such that before it gets refreshed. So one solution you can think of right now is you can actually refresh DRAM more frequently to get rid of these errors. And that's actually a viable solution, except the results that we have in this paper suggest that if you want to get rid of all of the errors, you need to refresh DRAM by 7 times more at a faster rate. OK, so why is this a scaling problem? Clearly, this happens because you have you have interference between different cells. And as you scale the circuit down, that interference becomes higher. So we tested chips from 2008 to 2014. I know even 2015 right now, it's not shown here. The first time error appears in the chips that were manufactured in 2010. Before that, there are no errors. Later, between 2012 and 2013, DRAM manufacturers were not able to contain these errors. And for good reason, because this requires a lot of testing, if you can imagine what the testing goes into it. And all of the chips that were manufactured during this period are actually vulnerable. And later, manufacturers started realizing it, and actually they have mechanisms to fix these errors. And we have this infrastructure where we tested DRAM. This is the old version of the this is the oldest version of the infrastructure, and we have a newer version. But I'll talk about some of these other works that I actually that we use to derive some insights into DRAM scaling. And this is the latest version of the infrastructure. I'd be happy to talk about this. And we're hoping that we'll put it into public use by putting the memory controllers out there. But the paper has a lot of results. So one interesting solution, one interesting part of it is, what is the solution space? You can imagine many, many solutions to this. Error correcting codes could be one of them. And SecDet actually doesn't correct all of the errors according to our results. And the solution we propose very briefly involves refresh. Basically, the idea is if you activate a word line with very low probability, activate the word lines around it, such that you minimize the risk of errors over the long run. And by doing this, you can actually get reliability guarantees that are much better than hard disks today. Yes.
Did you ask the memory vendors? Because isn't it true that if you look at memory built-in self-test, right? Yeah. That would do all this walking ones, walking zeros, and all that stuff, basically, that goes after coupling of the neighborhood cells.
That's right.
And if you combine that with retention test, basically, they would be caught, right? The only issue is that those tests cost a lot of money, and that's why. So did you talk to the DRAM vendors to see, like, why, what was their motivation for letting these tests not happen on the tester?
So maybe they didn't realize it. We have talked with it. They don't tell us why the errors happen clearly. But I think there can be tests that are designed, but they're very costly, as you said, right? And going forward, it's going to be a big problem testing these DRAMs, I think. But later, after we published this, Passmark actually included a hammer test in their memtest 86 program. So you can actually have that test, and you can run it on your real systems. And I believe going forward, this kind of failure mechanism will need to be tested to screen it out. But we'll talk about the DRAM testing in a little bit more detail later on.
The question I asked is, like, by doing this thing, were you somehow changing the specs of the DRAM by any chance? Like you're not, right? It should be,
Exactly. This is not supposed to happen in DRAM, because you shouldn't. This is a very predictable form of error, and you should not get that. Yes.
Why can't the chip just detect that it's being hammered and slow down the next request to give it a chance to solve?
So that's one of the solutions that we've discussed. How do you detect whether you're being hammered? Basically, you need to keep track of the number of hammerings that happen, and that actually costs a lot of hardware. I'd be happy to, yeah, it does cost. We described that in the paper, actually. So this probabilistic refresh doesn't cost any hardware, any state, except you do it randomly. And the problem is you need to know which rows are adjacent to this row. And today's memory controllers have no exposure to that information. Yeah. So you can do it within DRAM if you have slack in the timing, but it's very difficult to do it on the memory controller side. That's why I think we need some other interface to fix some of these issues. OK, so we can talk about solutions. And it's fascinating, actually, to talk about the solutions. But I'd love to. But one thing I will talk about is this is actually, it seems like a little hardware problem, but it actually affects a lot of the system security that we have built things upon. Basically, when we wrote the paper, the first sentence we had was memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. And we were pretty sure that you could design an attack to take over an entire system. And that's exactly what Google Project Zero did in March of this year. What they did was they exploited this bug to gain kernel privileges. And I'll copy from their blog post, basically, for this slide. They tested a selection of laptops, and they found that it's vulnerable to this problem. And they built two different privilege escalation exploits that use this. And you can read it in more detail. But the cool thing is what they did was they were able to induce bit flips in their page table as a user-level process in the page table entries. And you can actually induce a bit flip in your write protect bit or write enable bit that actually points to your own page table. As a result, you gain write access to your own page table, which means that you gain write access to your entire physical memory. That's how they were able to take over 50% of laptops. And recently, there was some research coming out of Europe where they showed that you could actually use the JavaScript to execute code remotely on some other computer that's vulnerable to row hammer bug, and you can take over that computer remotely. So it's pretty interesting, actually. And later, this became kind of popular, and people came up with funny pictures like this. And one of the quotes that I really like on the website, which really, I think, provides the insight to the security attack, if you want to gain access to that door over there, you keep hammering on this door enough times, and that door opens up, and then you gain privileged access to that door. OK, so let me recap the DRAM scaling problem. So I believe this is one evidence of the DRAM scaling problem. And if you think about it, if you take a step back, there's nothing new here, right? All of the memories, as they scale down, they have these effects. Flash memory, for example, is very prone to read disturb errors. And flash memory has a controller that corrects those errors. In hard disks, you have adjacent track interference, and there is a controller that fixes a lot of those issues. But in DRAM, we weren't used to these issues getting exposed, so we need some solution. But before that, let me talk about one paper that Samsung and Intel, two unlikely partners to write papers together. They've written this paper in the Memory Forum 2014 that we've organized with ISCA. And they've pointed out some of the challenges, which I will talk about later. And they've identified refresh as a big challenge and variable retention time as a big challenge. We'll talk about this in a little bit. But it's clear that the manufacturers are also seeing the problem. And the solution they've described is similar to what has been employed in other memories, basically co-architecting controllers and DRAM together, such that because the process or the device is not scaling very well, maybe you punt a little bit and you enable the system to scale by co-designing the system and the DRAM together. So that brings me, how do we solve the problem? I'll talk about three solution directions overall, and then we'll go into a little bit more detail. So the first solution is making DRAM and controllers more intelligent, fixing it, basically. Since we cannot fix it, well, maybe we can fix it at the device level and circuit level. I'm not precluding that possibility. But I think a good direction to explore is to design the system together with the DRAM, looking at new interfaces, new functions, and new architectures. The second solution direction, which is also promising in my opinion, is somehow trying to eliminate or minimize the problem. Basically, come up with a scalable technology that's much better than DRAM, that doesn't have these issues. Good luck with that, but I think this is really interesting to explore. Basically, this can open up new technologies and system-wide rethinking of storage and memory, depending on what kind of technologies you actually design. And the third solution direction, which may sound a little bit crazy sometimes, is to embrace it, maybe. Maybe we can design some memories to be not reliable and take advantage of the application-level characteristics and make use of these lemon memories. And I think that's really interesting, too, because this can open up new models for data management and maybe usage, as long as we can do it appropriately. And there may be other solution directions, but I think regardless of the solution direction you take, good solutions to memory scaling, in the end, will require software, hardware, and device cooperation, especially given the historical examples we have in other memories. So we need some rethinking across the stack. So let me very quickly talk about these solution directions, and I'll talk about an orthogonal problem, and then we'll go back to 2 solution directions. So what do I mean by fixing DRAM? Basically, you'd like to overcome the shortcomings that we have in the technology with what I call system DRAM co-design. This can open up new DRAM architectures, interfaces, and functions. And the good thing is industry is actually interested in doing something around this area. That has not been the case traditionally in memory industry. And we should do better waste management, more efficient utilization, since the resource is not scaling very well. So there are several key issues to tackle. I'll touch on some of them during the seminar. One is enabling reliability at low cost, fixing problems like row hammer. And we'll talk about that a little bit. The second is reducing energy such that we can scale the memory. And these are actually 2 sides of the same coin, if you think about it. You can enable more reliability by expending more energy. In fact, Apple's solution to the row hammer problem, Apple released a security patch after we written our paper and after Google's attack. In the security patch, what they've said on the web is they increase the refresh rate to actually fix the row hammer problem. The problem is, as you increase the refresh rate, you increase your energy, even though you enable reliable. So these are really 2 sides of the same coin. And improving latency and bandwidth is important. I'm not sure if I'll get to talk about this, but especially reducing latency, there's a lot we can do in this area in DRAM, because we're really wasting a lot of the latency. Our timing parameters are designed for the worst case. And reducing waste in capacity, bandwidth, and latency. That's, I think, very promising also. One thing that I will focus on that can help a lot, and an idea whose time may come if we do the right things, is enabling computation close to data, because we can actually potentially fix a lot of the issues we're having if we do this over here. We not only can enable computation, but also management close to the data. So I'll talk about some of the works that we have in this area. The second solution direction is emerging memory technology. I think this is very promising also. There are some emerging resistive memory technologies. And because they're resistive, they're more scalable because they're not dependent on this charge storage. And as a result, and they're also non-volatile. One example is phase change memory. There are also other examples, STT-MRAM, RRAM, resistive RAM. And these are expected to scale to much smaller nanometers. And ITRS has been projecting that 9 nanometers. At the same time, it was projecting 35 nanometers hard for DRAM. And they're expected to be denser than DRAM because these technologies can store multiple bits per cell by chopping up the resistance range, just like flash chops up the voltage range. The problem is a lot of these technologies have many shortcomings. The key question we're asking is, can we somehow enable them to replace, augment, or maybe surpass DRAM? And I'll talk about some of the works in this area. I think that's also a very promising direction. The third solution direction, which I will also talk about, is doing something that looks like this. This is a cartoonish picture. Don't take it so seriously, because it could be designed a different way, but designing hybrid memory systems. People have searched for universal memory for a long time. Universal memory is a memory that's good green in all metrics. But if we don't have green in all metrics, if we have some memories that are green at some things and red at some other things, and other memories that are green at some other things and red at some other things, yet other things, maybe we can combine them together somehow and design the hardware and the software together to manage the data allocation and movement to achieve the best of multiple technologies. I think this is a very promising direction going forward. You can actually have DRAM of different types as well to be able to do that. Let me give you one very quick example. This is just as a teaser, if you will. But one of the promising directions, in my opinion, is to exploit application-level fault tolerance. If you understand your application very well, you can potentially mark your data or understand your data based on its memory area vulnerability. So if you inject a bit flip to that portion of your data space, sometimes it doesn't matter that much because your application doesn't crash. Maybe a pixel changes. Maybe no one cares in the end. But sometimes it matters a lot. Maybe you change a pointer in your program, in your index of the database, and that actually crashes the entire system. So if you can somehow classify your data as vulnerable and tolerant, you can perhaps take advantage of this at the memory level, design reliable versus low-cost memories. Maybe you don't care about the row hammer faults as much over here. And you can actually take advantage of this. So we actually have a case study of this with Microsoft's web search workload. In a lot of data centers, the ECC memory is used so that you can protect for the errors. But this way, you can get rid of a lot of the cost in memory by making some of your memory low cost. That way, you can reduce the hardware cost reasonably while still achieving a reasonable single server availability target. So I think this is just one example. This is just scratching the surface. One example of a heterogeneous memory. In this case, it's heterogeneous in terms of reliability, but you can imagine heterogeneity in terms of different technologies as well. And this was all done manually by manually modifying the application. It doesn't work for all applications. So if you actually do it for graph processing applications, it's actually very difficult unless you go very fine grain in the data structures. Okay, let me briefly talk about an orthogonal issue, and I'll talk about more specific solution ideas. And this orthogonal issue is really important in my opinion. That's why I didn't want to remove these slides. And the problem is you have this memory bus that's shared, and the cores interfere with this memory bus when they access the shared main memory. And it's an interference problem. If you don't somehow control the interference, which is actually the case in most systems today, you can actually get a vulnerable system. Basically, the memory controller can be optimizing for locality in the row buffers of main memory, and an application may be very good at exploiting that locality. As a result, this application that is doing random access that has bad locality will be deprioritized by the memory controller if your memory controller policy is to optimize for locality without being application aware. And as a result, if you have unfair policies, you can have an uncontrollable, unpredictable, and vulnerable system. And this becomes more important if you're running many more applications on top of on your node where you're sharing the memory bus. So how do you actually fix this problem? We've been looking at this. I'd love to talk about this with other people, but very quickly, you need to design a quality of service aware memory system where the hardware provides at least some sort of guarantees. It provides a configurable fairness substrate, application aware memory scheduling policies, ability to partition memory, awareness of the memory to the higher levels, and throttling mechanisms such that you don't overload your memory. And software can be designed to configure these resources to satisfy different quality of service goals. So it's a hardware-software cooperative problem. And this problem is going to be even more important because we're designing even more complex systems. Basically, we have not only cores, but GPUs and hardware accelerators. They all have different demands from the system, and they all share different parts of the memory system. And the memory is also getting more complex. Basically, we have hybrid memories and hybrid memory controllers that are controlling them. The key question we're asking is, how do you allocate the resources in the memory system to these heterogeneous agents to mitigate the interference that's happening across these different agents and provide predictable performance to those agents that actually need that performance? So one solution direction, very quickly, this is my last slide on the quality of service. I think we've been looking at more best effort approaches, but I think going forward, strong memory service guarantees is really important. And the way we're thinking about the problem currently is, if we can somehow estimate the performance loss you have or slowdown you have for an agent when you're running together with other agents, and if you have an online model that can estimate this accurately, you can actually use this in many ways at the system level. You can expose this to the operating system, for example. The operating system now has a very good idea of, oh, this application is slowing down a lot because it's sharing memory resources with the other application. And if you design the mechanisms, resource partitioning mechanism or prioritization mechanism in the caches and the interconnect and the hardware, you can actually use these models to drive the partitioning such that you satisfy the performance requirements of a given application. You can now say, oh, this application shouldn't be slowed down by 2x, regardless of whatever I run it with. And if you have this model, and the model is accurate, you can try to satisfy that. And if you cannot satisfy that, then you punt the problem to the higher workload scheduler, and the workload scheduler does something else. Today, we don't have this guarantee from a single node. As a result, I think we're underutilizing the single nodes a lot, because if we want to provide these guarantees, we need to be conservative, because hardware doesn't provide any guarantees underneath. Now, it's changing in the cache level. Intel actually has the quality of service mechanism such that you can partition the cache. But going forward, we need to look deeper into the memory. Of course, you need to do this all the while providing high system performance. This goes without saying, because fairness or quality of service is not a problem if you don't care about performance. You can design a 1,000-core, 1,000-agent system and just run one agent on the system, and everything else becomes underutilized. So I'm not going to talk about this, but we have a mechanism that's coming up. It'll be published in Micro in December that talks about an application slowdown model that achieves about 10%, an error of within 10% to do the slowdown estimation in caches and main memory. Okay. Any questions so far? Am I speaking too fast? Okay, cool. Now we can actually, I can increase my speed and you can throttle me back.
I'll throw a question.
Yeah, sure.
So the solution to aptly is just refreshing more often. Really, I don't think refresh takes a whole heck of a lot of energy. It seems like some of these other solutions might take a lot more energy than just refreshing a few more times.
So
yeah, it depends on the solution. So refresh, I agree. Today, it may not take a lot of energy, but going forward, we'll talk about it. It will take more energy. So it's not a scalable solution going forward, but it's probably a good stopgap solution for today. And I don't know how much they increase the refresh rate. They don't talk about that in that web post. Maybe 2x. That's my guess, but maybe 4x also. But 2x in our experiments, 2x actually doesn't get rid of all the errors, increasing refresh rate. But I think a targeted refresh, more probabilistic refresh, actually is very negligible in terms of energy and performance. Yes?
So in your very first solution, you mentioned the better waste management in terms of capacity, bandwidth, etc. Do you have anything specific in mind?
Yes, I'll talk about some of those here. Yeah, basically the first part I will dedicate to new memory architectures. I'll talk about rethinking DRAM. We have a lot of work on rethinking flash memory also. We have a very similar infrastructure for flash memory where we gained a lot of insights thanks to some of our industrial partners. But I'm not going to talk about that, but in a little bit. The second direction is enabling emerging memory technology. So I'll dedicate some time on hybrid memory systems and single-level memory and storage. So back to the future, maybe a little bit. But I'm not going to talk about the system-level memory and storage quality of service, although that's a critical problem, but we just don't have time. So hopefully, at the end of this talk, you'll have a lot of hope that we will fix DRAM somehow, but we'll also enable these emerging memory technologies somehow, and maybe design a predictable system. Let me jump into the first one. There's a lot to talk about DRAM, actually. We've been focusing on this for the past 4 or 5 years. And I'll probably cover these three very quickly. Well, not very quickly, but these three. Let me start with in-memory computation, because I think this is an idea whose time has come. And why do I think its time has come? Because we're feeling this technology push from DRAM. DRAM scaling is very difficult right now, and vendors are very interested in examining new solution directions. For example, the paper that I mentioned from Samsung and Intel, one of the solutions that they propose is putting ECC inside DRAM, in DRAM ECC. This was a big no-no for vendors for a long time. You don't want to modify the subarrays because that has a lot of overhead. But now they're thinking of putting ECC because they're feeling the heat. So if you actually can do things like that, if you can put a logic layer underneath DRAM, which some vendors have explored, like Hybrid Memory Cube, then we can perhaps explore even more interesting solutions that can change the model of execution that we have today. And the second is, in no time in the system design we've had in decades, we were so pressed by data movement and storage being a bottleneck so far. Basically, systems are energy limited, data movement is the biggest cost, and applications are extremely data intensive, both bandwidth and capacity. So there's this application push also that's driving us to do more on the memory side, in my opinion. And I'll talk about two approaches. And this is a really old idea. One of in the late 1960s, Harold Stone from IBM Research, actually, he published the first paper, Logic and Memory. And at that time, that's in 1970, at that time, the idea was if we can put processors inside DRAM, we can do a lot more. I'm not going to talk about that. I think that's going to be very difficult, even though some of those early works were really interesting. I think we should think a little bit differently, perhaps, today. And one approach that has a lot of promise, and surprisingly, it hasn't been examined as much, is minimally changing DRAM. I think we can minimally change DRAM to enable simple yet powerful computation primitives. They can be limited, but DRAM can be used as an accelerator, especially when you need it significantly. So I'll talk about this a little bit. And the second solution direction, which I will not talk about, is to exploit the control logic in the 3D stacked memory, which hopefully will exist such that you can enable more comprehensive computation near memory. So this may be a more costly approach. So let me first focus on the first one, but I'll talk very little, if we have time, at the end of the in-memory computation part. So what do I mean by minimally changing DRAM? So when we first started, we were thinking about what is minimal changes? What is DRAM good at? What can we do that we can provide? And the first thing is, you can imagine, is bulk data copy, actually. If we can do copying internally in the DRAM chip, we can save a lot of energy. Now, granted, this is cheating, this is not computation, but even this is not possible today. So let's talk about the problem first. If we want to copy one page to another in memory today, we go through the CPU as the intermediary. Basically, you need to bring the source page byte by byte all the way into L1, the destination page byte by byte all the way into the L1, do the copy, and write the destination page all the way back into memory. Now, with a 4 kilobyte, this is still bad, but if you consider 1 gigabyte page, that's actually overwhelms the system. Now, you don't want, hopefully you're not doing copies with 1 gigabyte pages, but that could happen actually. Initialization is a very special form of copy, and initialization can consume a lot of cycles. But this is high latency because you do round trips across this most important system resource, perhaps. This consumes high bandwidth on the data bus. This causes cache pollution, but you could eliminate that through the DMA engine, perhaps. This causes unwanted data movement, especially if you're not using the destination page at all soon. Basically, if you want to do this copy with the DDR3 technology for a 4 kilobyte page through the DMA engine without taking into account the overheads of setting up and tearing down the DMA, basically it takes 1,046 nanoseconds and 3.6 microjoules. Now, wouldn't it be nice if we had the option in the system to tell the memory to do this, and the memory doesn't bother anyone else? This would be low latency, because I'm going to give you a mechanism, multiple mechanisms actually. This will cause no bandwidth utilization on the data bus, which is a major bottleneck. This would cause no cache pollution, but you could eliminate that if you want today. And this causes no unwanted data movement, so it saves energy. And I'm going to show you a mechanism which, in the best case, reduces this 1,046 nanoseconds for a 4 kilobyte copy to 90 nanoseconds, and the 3.6 microjoules to 0.04 microjoules. And the idea is actually really simple. If you know about how DRAM operates in the subarray level, this is the DRAM subarray. If you want to read 1 byte over here or 8 bits over here, you really need to activate an entire row. And that row, let's say, it's the same as page size, 4 kilobyte. You can activate this row, and then you need to issue a read command to read the entire 8 bits out of this row buffer. So we're going to take advantage of this row level operation to do row clone. The idea is, if you want to copy one source page to a destination page in DRAM, first you activate the source row, which brings the data into the sense amplifiers. Then you send a command that deactivates the source row, but activates the destination row. And once you do that, the data in the sense amplifiers actually start driving the destination cells. As a result, you've used the sense amplifiers as an intermediary to do the copy. Basically, by doing 2 consecutive activates, you can do this copy really fast, as long as the source and destination rows share the sense amplifiers, which means that they are in the same subarray. And you cannot do this in today's DRAM chips, unfortunately, because it's not enabled. But this is very, very little cost to do.
Sense amps, because there is a DRAM memory built-in self-test, and you can take advantage of that engine maybe and just simply read it, because the BIST controller should be able to read and write, right? So they already have the registers and use that to just read and write back.
That's right. So I think the BIST circuitry actually goes outside the subarray. So it will, you can do it actually, I agree. It'll be slower than this. Yeah. Absolutely, yes, absolutely. And the other solutions are going to resemble that. Yeah, I agree with you, certainly. So this is the fastest you can get, I think, in the subarrays. And it's actually 90 nanoseconds. It's 2 consecutive activates. Well, I had modified the slide, but that's not 0.01% area cost, by the way. The 0.01% comes from generalizing it such that you can do it in the entire, within the chip. So clearly, this is not general, because it's limited to subarrays, and actually operating system has no visibility to the subarrays. That's, but we'll talk about that. So intra-subarray copy is just 2 activates. But we would like to do it even if the data resides in different banks. So what we do is to have pipelined internal read and write through the data bus internally in the DRAM. Basically, you set one bank to read mode, you set the other bank to write mode, and you can do arbitrary length data copies by doing this. And the hardest part, which I'm not going to talk about, where you can actually utilize the BIST circuitry, is if you want to copy data from one page over here in one subarray to another page in another subarray in the same bank, because they share the global bit lines, you cannot do that as fast as this. So what we actually do is we use interbank copy twice. But you could actually use the BIST circuitry also. So all of this is 0.01% area cost with our models of DRAM. So what is the savings you get? Clearly, the savings you get depend on where the source and destination pages are. And hopefully, if you expose this to the system can allocate the pages such that you get the maximal savings. That's one of the things that I will talk about in a little bit. But basically, if the source and destination are in the same subarray, you get 11 times latency reduction. And the energy reduction, this is the DRAM energy only, is 74x, because you're not exercising that interconnect between DRAM and memory. And clearly, if it's between different banks, you save less energy and less latency, but still you gain. The worst case, you still save energy internally. So what is the impact on the application performance? These are probably not the best applications, and take all of these with a grain of salt. But basically, it improves performance. Fork, for example, is the poster child for this, because it does a lot of copy on write in the end. And if you're able to allocate, so one thing, if you're doing copy on writes in the operating system, and if the operating system has visibility to the DRAM topology into the subarrays, the operating system can say, oh, when I'm writing to this page, I need to do a copy. At that point, I'm going to allocate that page from the same subarray as the source page. Today, we don't have that visibility. We really need interfaces that are much better into memory such that we can do this kind of system-level optimizations. So if you do that, actually, you can gain a lot of performance. And the paper has a lot of analysis. So system boot up, for example, you can gain a lot of performance. Basically, the performance improvements correlate with the amount of copying and initialization that you do. So initialization is something that I very briefly touched on. Initialization is really a special form of copy. Basically, you want to zero initialize a huge chunk of memory, you zero initialize a row, and then copy that row to other rows. That way, you can actually get rid of a lot of the initialization penalty, too. And the performance improvement is even more in multi-core systems, because when one application or one thread is doing copies, you're freeing up the memory bus such that the other thread can actually access memory. So let's assume that we had this row clone idea, and I think the DRAM manufacturers are really interested in small changes like this that can actually impact a lot of applications. We still are not done clearly, right? You really need to have an end-to-end system design to take advantage of something like this. And this is true for all in-memory computation that I'm going to talk about. But I'll use row clone as an example. You have this row clone-enabled DRAM. How do you take advantage of it? First, you definitely need to communicate occurrences of this bulk copy and initialization, actually, it doesn't have to be bulk copy if you're doing interbank. It has to be bulk if you're doing subarray across the layers. So you need to have mechanisms for this. Fortunately, some ISAs actually have this today. The x86 ISA has a repeat prefix, which you can use with copying instructions. Ensuring cache coherence is critical, and we have some mechanisms for that I'm not going to talk about, especially if you want to use this in the general purpose domain. In the special purpose domain, so perhaps you can ignore some of this early on. But going forward, we need better mechanisms, because this can actually dominate the costs of doing computation in memory. How do you maximize latency and energy savings? So how do you make the operating system and the applications aware of the topology of the DRAM and the computation capability such that you can get the best advantages? As I've described, if you make the operating system aware of the subarray or the DRAM topology, you can get a lot more done. And finally, we don't want to do this always in memory. In fact, if you do row clone for all page copies, you lose performance in some applications. Sometimes you do want to do this on the processor side, especially when your caching is very effective. So we want to have mechanisms to understand when to do what. Sometimes row clone, sometimes doing the copy internally in the processor. So that's also very important. And the paper has some detail related to that. So where are we taking this? I think we're designing all these different accelerators that are very good at making us process data efficiently. But basically, I think this direction is really thinking of memory as similar to a conventional accelerator. Memory is good at some things. If we can figure out what those some things are, we can put some specialized compute capability in memory. And we can think of that as an accelerator for those computations. And it's actually a very different accelerator from what we have here, because it has access to this huge data store. And it's also sitting on the other side of the memory bus. All of these accelerators are bound by the memory bus if you're dealing with huge data. So one of the things that I will briefly touch upon, this is something we deal with in one of the ISCA papers with 3D stacked memory, but it's a general problem. If we can somehow enable in-memory search or graph analytics or big data analytics, I don't like using that big data term, but big data analytics, how can we do it? I'm going to list a lot of questions over here, but our ISCA paper has some answers. Basically, let's say you have this database or graph stored in memory in your different subarrays. We'd like to send a query to memory with some interface over here, and the memory does the searching in its subarrays and returns back the results such that the CPU can focus on this. There are many questions here. The interfaces that we have today do not enable this. We need more scalable and flexible interfaces. What is the right partitioning of computation capability? What is the right low-cost memory substrate? How do you actually build this comparison? I just gave you copy, right? Hopefully, I'll give you a little bit more hope in the next few slides. But you need to do more than just copy. If you have the logic layer inside the 3D stack, then you can actually do more. And that's what our ISCA paper is about. You can actually gain 14x performance improvement and reduce system energy by 10x if you have a graph analytics engine that's sitting in an interconnected set of 3D stacks. I'm not going to talk about that. That's the more intrusive approach, because you need a different programming model to take advantage of that, actually. So what memory technologies are best enablers? DRAM is very interesting to examine, but there are other technologies that integrate much better with logic. And once we have this, how do you actually rethink or ease search algorithms or different algorithms and applications? In fact, we had this problem with row clone. We were actually searching for applications. And when we talk with people, they say, oh, we avoid those copies as much as possible. So they actually jump through hoops in their software such that they don't exercise the bulk copies. As a result, this complicates the software a lot, actually. But if the copies are a lot cheaper, maybe there's a different way of designing the software which makes life easier for the programmers. And that's true for other computations also, I believe. So this is actually a slide from my student Vivek Seshadri, who developed the idea of row clone. But basically, we need support across the entire system. This is from his proposal, and he's completed all of this, so he's ready to graduate, I believe. The blue parts. Yeah. But basically, we have a paper coming up on in-DRAM gather scatter. And I'll hopefully give you some hope by talking about in-DRAM bitwise operations. But we need cache coherence support, and we also need some virtual memory support that I'm not going to talk about. But let me give you a little bit more hope, because computation is, data movement is kind of cheating, because you don't do any computation. But I think there's a lot of potential for computation in DRAM also, even within the core of the subarray. I think external part, like the BIST part, is very interesting also to examine. But in the core, you can get even more benefits. And the idea is, how do we do in, and OR? And I'm going to assume an idealized circuit here. Basically, if you have these A, B, C, rows A, B, C, and if you concurrently connect the word lines to the bit line, what you really get is a majority circuit of A, B, and C. Now you can actually do a majority circuit operation in the entire A, B, C rows. But the other interesting thing is you can rewrite this equation like this. You can take out C, and now this can be your control row. If C is set to 1, all ones, now you get the OR of A and B. If C is set to all zeros, you get the AND of A and B. Basically, we have an analog computation mechanism that can do AND and OR in DRAM, assuming you can design these really nicely, of course. It's destructive, absolutely, yeah. So I'm going to give you the instruction semantics in a little bit. It destroys, in the end, the result becomes whatever you have over here. So you can actually imagine an instruction that looks like bulk AND, which is, semantics are like that. And this is one way of implementing it. You can reserve a row to 0, reserve another row to 1. And you can have designated rows for triple activation. So the cost of this is triple activation. And you want to limit that because you don't want to be able to do triple activation in arbitrary addresses in the subarray. So if you actually reserve this to a very small portion, you can actually do the AND and OR in that small portion in the subarray. And this is how it works, basically, instruction. You first row clone the data into this designated 1 row, row clone B into the designated 2 row clone R0, which is the AND, in this case. You need the control row into D3. You activate, do the triple activate, and then row clone the result into C. And now D1, D2, and D3 all have the result. So if you do this, what are the benefits you get? Basically, we see significant improvements in AND and OR throughput compared to the state-of-the-art mechanism, which is doing the AND and OR inside the SIMD units, Intel AVX over here. So Intel AVX actually works really well. This is the size of the vectors to AND or OR, and this is the throughput of the AND operations in this case. If your vectors are really small, you run out of the cache, so your SIMD units are very effective, actually. You get very high throughput. But if your vectors are really large, the throughput of the SIMD units reduces because now you're memory bound. Whereas if you're doing this operation in memory, you can sustain the same level of throughput, which is actually 20x higher in this case when your vectors are larger. And you can actually scale this by doing in many banks at the same time. As your data size scales, you can actually do it concurrently in many banks. And the energy reduction is significant. And this paper has a more detail, actually. You get 50x energy reduction because you're not moving data out of the chip. So we've actually tested this on some real workloads, a database that does range queries that uses a lot of ANDs and ORs to actually do the selection. And it uses the fastbit library, which is a fast library for doing AND and ORs. We ported that library to use this in our simulator. And you can see significant performance improvements in many range queries. And the paper has a lot more detail on this. Yes?
Do you believe the variation between the cells are controlled well enough to be able to do this reliably?
So that's exactly why I said assume an idealized circuit. So I think if you reserve 3 designated rows, I believe it could be designed. But then I think that's up to the DRAM designers. That's a part where I cannot design it. But I believe the good DRAM designers will be able to design it. Yes.
How do you handle the alignment issues within the bus?
So that's an excellent question. That's the limitation of this model. Basically, your data, you AND and OR everything over here. But we're developing more primitives, like NOT or some XOR or masking that we can do potentially in memory. But I don't have those results yet. But yes, for this, you need to operate at the bulk level.
And so That, if you did it in memory, if I call it in-memory array versus an in-memory structure where you put in a little bit of logic basically outside your memory array, what would be the sort of the difference in performance / energy? This is sort of in an ideal situation, this gives you the best, right?
That's right.
It has its sort of inherent limitations in like
That's right.
circuitry stuff basically. Versus if I just was not as adventurous, but still I put in some additional stuff inside the memory chip to do stuff.
Yes, it's closer to the BIST logic, closer to the outside.
Or whatever,
Sure.
how much of these benefits I can still continue to get.
So I think the benefits are similar to the row clone benefits. We have not, we're actually exploring that right now, but the benefits are, you remember the interbank copy? Right. I think the benefits are similar to that. Exactly, it's of that order. So it's still significant, but it's not 20x. Yes.
What applications show benefits of huge vector ANDs?
So these are some range queries in a database that uses a fast bit library. I don't remember the exact thing, but the paper has the details. And I can send you more information. This is a shorter version of the paper.
Version with.
That's an excellent question. That's the next step.
Consider the logic this support is universal.
Exactly. You become Boolean complete, basically, right? Yeah. So that's our goal, actually. Basically, where we're taking this, we want a bulk computation model in memory. We have some mechanisms to the inversion. It's not as easy as AND and OR. But there are different ways of thinking about it and doing it. But maybe I'll talk about that later at some point. But I think this is very interesting. Maybe I should put the bulk in parentheses because, as Subhashis mentioned, there could be other ways of doing the computation internally in chip. But this basically requires new memory and software interfaces to enable in-memory computation. And at some point, I think I'd love to examine new programming models, algorithms, and compilers, perhaps. Because this can actually, if you have a bulk computation model in memory, you can actually take advantage of a lot of things, in my opinion. So I've talked about the first approach, basically minimally changing DRAM to enable simple yet powerful computation primitives, and hopefully giving you some hope in that direction. There's a lot more you can do with the 3D stacked control logic layer, and I'll point you to these papers. Basically, we've examined what is the minimal thing that you can do if you have a 3D stacked logic layer without changing the existing programming model, keeping the sequential programming model, without changing the virtual memory substrate, without changing the cache coherence mechanism significantly. And we call it the PIM-enabled instructions. Basically, you have an instruction, PIM add. You can execute it in memory or in the processor. And it's virtualized, it's cache coherent. And that actually buys you some benefit. And this was the second thing that we've explored that's also published at ISCA. Basically, the idea is, what is the thing that you can do if you can change things maximally? In this case, you can think of the 3D stack memory as an accelerator. How do you map the graph processing application to it? What is the programming model? We don't assume virtual memory in this case, for example. So that actually shows a lot of benefit also that I mentioned earlier. I don't have time to talk about this, but I think this is a very promising direction as well. OK, let me jump into refresh, and then I'll switch to the other direction, which is emerging memory technologies. How much time do we have left? 17 minutes. OK, refresh will be really quick then. OK, I want to talk about refresh because this is one of the major scaling challenges. If you talk to a DRAM designer, probably they will tell you that this is the biggest headache they have in DRAM. But the problem is DRAM capacitor charge leaks over time. And the memory controller needs to refresh each row periodically to restore the charge. And today, you need to refresh activate every row every n milliseconds, typically in 64 milliseconds. That's probably going to go down. There are many downsides to this: energy, performance, quality of service impact. But I'll talk about one thing. Refresh rate actually limits DRAM capacity scaling. So this is from a paper that we did in ISCA in 2012. This is device capacity on the x-axis. This is the percentage of time you have to spend to do refresh, basically the throughput loss of the device due to refresh. Today, it's about 8%. If the scaling trend continues, and I'd be happy to talk about the assumptions that go into this, it's going to be about 50% if you design a 64 gigabit DRAM chip. And energy, percentage of DRAM energy spent refreshing, today it's about 15%, let's say. And again, you can argue with the numbers, depending on your utilization and how much you're accessing the memory. That changes. But with the same utilization, at 64 gigabit node, you'll be spending 50% of your DRAM energy on refresh, if nothing changes. And this is a little bit scary because we're designing this huge memory chip, which we cannot access half of the time, And half of its power is really energy spent on refresh, keeping the data. I'll talk about one promising direction. I'll talk about the issues related to this. Basically, we don't need to design the refresh for the worst case. If you look at the retention time profile of DRAM, due to the variation in the circuit, you have this retention time profile. Today, we're refreshing everything every 64 milliseconds. But most of memory doesn't need to be refreshed for 256 milliseconds. So if you can somehow figure this out, you can actually reduce your refresh rate by 75%, or number of refreshes by 75%. And that's the idea. I'll give you some results first and talk about what are the challenges in enabling this. And this is an old observation. Many people have written papers in electron device letters. But with our infrastructure, we've shown that this actually holds true for many, many DRAM chips also. The idea we've looked at is refreshing rows containing weak cells more frequently and other rows less frequently. And this requires 3 steps. Very quickly, you need to profile the retention time of all rows, figure out the minimum retention time of all rows, and store the rows into bins by retention time in the memory controller, if you're doing this in the memory controller. And you can have really simple mechanisms by using Bloom filters to do that. I'll refer you to the paper. And the memory controller can now refresh rows in different bins at different rates. Now, if you do that, you can get significant refresh reduction, almost 75%, at very low hardware costs. You can reduce DRAM dynamic and idle power significantly, and you can get significant performance improvement. And actually, benefits increase with DRAM capacity. So energy reduction increases to 50% at 64 gigabit node. Now, the most difficult part turns out to be the profiling step. And that's exactly why DRAM manufacturers are having a problem, because this profiling, figuring out the test, like what is the minimum retention time, is very difficult. And it's difficult, and I'll refer you to especially this paper over here. But it's difficult due to the problem that the 4-page paper that I mentioned from Samsung and Intel talked about, the variable retention time problem. It turns out a DRAM cell, the refresh, for example, first of all, is data dependent. That's one issue. It depends on the data around you, how much you need to refresh this particular cell. But it also is dependent on a random process. Basically, for a long time, a DRAM cell can retain data for hundreds of seconds. And later on, charge gets trapped in the cell, and your leakage accelerates significantly, and your retention time tanks to 8 milliseconds. So you have this bimodal behavior in many DRAM cells. So you need to test the DRAM cell long enough such that you get to the minimum retention time states, which could be days and days and days, according to our results. This is actually getting worse with DRAM scaling. That's why VRT is one of the biggest issues. And that's exactly why DRAM manufacturers are really interested in putting in DRAM ECC, error correction codes, today.
The temperature dependence, this constant over different batches?
Yeah, so temperature depends actually.
That's a very well studied and examined effect. Refresh rate, you need to refresh more frequently as temperature increases. And that's already employed actually in some DRAM technologies, LPDDR, for example. Okay, so I'm not going to talk about this problem, but this is a fascinating problem. So how do you actually solve this problem, given that you need to test DRAMs for days and days? One option is to say, oh, DRAM manufacturers figure this out. I think it's going to be very difficult to actually do that. The thing that we argue over here is more online profiling of the system. And actually, there's one other reason why it's hard for the DRAM manufacturers to do this, actually impossible for the DRAM manufacturers, in my opinion. Once you solder the DRAM chip on your board, you expose it to very high temperatures, and that changes the retention time profile. And this is actually becoming worse with the scaled, smaller technologies. So the solution we're pursuing, and I don't have all the answers, is to do more online profiling of DRAM in the field. I think this can actually fix a lot of the issues that we have. Initially, protect DRAM with ECC, maybe in DRAM ECC. And over time, while you're running the system at boot up, plus during the execution, you periodically test parts of DRAM and do optimizations. You can adjust refresh rate, reduce ECC. You can determine the latency characteristics of different rows, adjust the latency. You can actually look at data patterns. If you're storing zeros, maybe you don't need to refresh that row. You can skip a lot of refresh. So you can actually do a lot more optimization, specialize it to the computation that you're running, if you can enable something like this. But clearly, if you would like to enable something like this, you need different interfaces and all kinds of mechanisms to keep the performance overhead and energy overheads low. But this is where what we're looking into going forward with the infrastructure that we have. So I'm going to skip the latency part, even though it's very exciting, in my opinion, because of this graph. We've focused on capacity so much, but the latency is not improving. But I'd be happy to talk about the solutions later on. But let me move into this one, which is also exciting. So it's hard to pick from multiple exciting things. But I'll pick this one. So let me talk about the second solution direction, which is enabling emerging memory technologies. And this is actually very promising, in my opinion, because there's some resistor memory technologies that seem more scalable than DRAM. One example is phase change memory, which you may have heard of. basically, it's actually a really old technology, right? It's used in the rewritable CDs, except we exploit something else, the optical reflectivity of the different phases of the material in rewritable CDs. Basically, phase change memory stores data by changing the phase of material, chalcogenide glass, and data is read by detecting the material resistance. And recent advance in the read devices over here, the access devices basically, has made it to be able to do this, to detect the resistance reliably. As a result, it's become interesting. In rewritable CDs, you basically shine light on a cell. As a result, you get different optical reflexivities, and now you can detect 0 or 1. But that's a very slow reading process, clearly. So you want this other read device that can detect the material resistance. And it's expected to scale to much smaller nanometers. It's prototyped at 20 nanometers. And it's also expected to be denser than DRAM. The key problem is these have many shortcomings. And this is just one example. Can we enable them to replace, augment, or even maybe surpass DRAM? Very quickly, charge memory is difficult to scale because it's difficult to place and control charge. And reliable sensing becomes difficult as charge storage unit size reduces. This is true in flash. This is true in DRAM also. Whereas resistive memory technologies do not rely on charge. Phase change memory, you inject current to change the material phase, and you detect resistance of the phase. In STT MRAM, you inject current to change the magnet polarity, and you detect resistance compared to a reference magnet. And in memristors, RRAM, or ReRAM, you inject current to change the atomic structure, and resistance is determined by the atom distance. So they have very different mechanisms, but in the end, they're all resistive. I'll focus on phase change memory because we've been looking at that for much longer. But I think other memory technologies are very, very promising also. So I'm not going to take sides on any technology. I'm going to look at the architecture and system level effects. Yes.
Which type is the new Intel crosspoint memory?
That's a great question. So I don't know, and I don't know if it's real. But my suspicion, based on all of the readings, is it's phase change memory, actually. But I'm not sure.
Intel Developer Forum, Micron gave a great presentation. They said they dropped phase change memory and went to ReRAM.
Okay, so maybe that's it.
I don't know. My suspicion was phase change memory, but it could be RRAM also. I may be wrong.
And you can see the presentation on the Intel Developer Forum.
Okay, so they actually said that.
Oh, it's in the presentation.
Okay.
It's online.
I think they said some kind of resistive memory. I do not think they said RRAM.
Oh, they didn't say RRAM? Okay.
I don't think so.
They said ReRAM.
Okay. Oh, they said ReRAM specifically. Okay.
Yeah. I'd love to get that link from you sometime. Please. Thank you. I appreciate it. Okay, so let's look at the architectural aspects. I think so. The pros and cons of cons over DRAM depends on what technology it is. So phase change memory, you get hopefully better technology scaling, better capacity and cost in the long run. You get non-volatility, and you get low idle power. Refresh problem goes away, which is actually nice. That's the key scaling problem with DRAM. The problem is you have higher read latencies and write latencies, higher active energy for reads and writes, especially for writes. And you get lower endurance. A cell basically dies after some number of writes, which is similar to the flash. And you have some other reliability issues, right? Resistance drift, but the time scales are much higher than refresh as far as we know today. So it's clearly challenging to enable phase change memory as a replacement for DRAM. We'd like to mitigate the shortcomings and find the right way to place phase change memory in the system. Very quickly, I'll go over our thinking over the years. This is actually a slide from 2008 when we first started looking at this. We asked the question, how should we organize phase change memory-based main memory? And our first idea was, some memory in the system will remain as DRAM, some memory will be PCM. And in this case, how do you partition and migrate data between PCM and DRAM becomes a problem. I'm going to talk about that later on. But we were more aggressive at the time. We wanted to examine the implications of this, at least in terms of performance and energy to begin with. So we wanted to look at the pure PCM-based main memory. So we did this study that was published in ISCA 2009 where we surveyed prototypes of phase change memory across many different device and circuit level conferences and tried to derive some parameters to use for a phase change memory that's at feature size 90 nanometers. And this is actually a harder task that's said than done because none of these papers agree with each other if you look at it. But we derived some parameters that are reasonable, in my opinion. I can never be sure, but these are the latency parameters. You're looking at a memory that's 4x slower in terms of reads compared to DRAM, 12x slower compared to DRAM in terms of writes. This is the energy increase. Writes consume 43x higher energy, and endurance. A cell dies after 10 to the 8 writes to it. And a cell dies because you actually, as you inject current and increase the temperature significantly to melt the material, 650 degrees Celsius, contacts degrade. As a result, you have this endurance problem. But basically, if you take a system that uses DRAM and magically replace every single DRAM cell with a phase-change memory cell with those properties without changing anything in the system, this is what you get for these applications. You get 60% performance degradation, you get 120% energy increase, and your memory dies after 500 hours. So it's clearly you don't want this as your main memory without doing some modification. So you can read this paper. We've developed some techniques for buffering. Basically, if you have this kind of memory as your main memory, you'd like to do enough buffering such that you don't access the memory, or you minimally access it. And if you do that, your results become better. 20% performance degradation compared to DRAM. Energy becomes on par with DRAM, but take this with a grain of salt. All energy modeling is, of course, difficult with an emerging technology. And average lifetime becomes 5.6 years, which is better, but maybe that's not what you want, because you don't want to be bound by the average, right? So I think this is actually going to be difficult with some memory technology that looks like this, using it as main memory. Because worst case lifetime is actually much shorter. You have no guarantees. You can actually have an attack program that can kill your memory. Intensive applications see large performance and energy degradations, and maybe we use optimistic PCM parameters. I don't know yet. But I think going forward, this hybrid memory systems is a very interesting solution direction. Can we somehow architect memory systems that look like this, or maybe have DIMMs that have multiple types of technologies, maybe have 3D stacks that have multiple different types of technologies, and manage the data allocation and movement. So we've looked at this in the context of DRAM and PCM. Very briefly, I'll give you results. I'm not going to go over the detail, but the key idea is somehow identify your data that's better to place at DRAM and better to, and identify other data that's better to place at PCM. So what's better to place at DRAM? Latency critical data. And data you can access as fast in PCM as in DRAM. You don't want to waste your DRAM space in it. And if you have streaming accesses, actually, you can keep them in PCM because you can read out of the row buffers, and your bandwidth can be as high as DRAM if you have streaming access. In fact, all you're doing is all you're doing is streaming, you can have a memory hierarchy that's composed of very slow circuits, like tape maybe, and design a lot of buffers in between such that you can stream through. But basically, that's the idea. Somehow you mark the data in hardware in this case, and you place the data intelligently. So if you do this, you're kind of in the middle. Compared to, this is 16 GB PCM performance, this is 16 GB DRAM performance. This hybrid memory with intelligent data management gets you kind of in the middle. So we're still not there yet. So there's a lot more headroom to do research in this area, in my opinion. So I'm going to skip this, but STT-MRAM, we examined STT-MRAM as part of your main memory. And the results actually are better because the cons of STT-MRAM compared to phase-change memory, at least at this point in time, is much better. You have higher write latency, but you don't have the read latency problem. You don't have the read energy problem. And you don't have the endurance problem. And as a result, your performance loss is not as high, and your energy savings are much higher. And if you're interested, you can take a look at the paper. But let me tell you a little bit about other opportunities, and then circle back, and then we'll conclude. I think it's a very exciting area, actually. Regardless of whatever technology it is, enabling some of these emerging technologies is really important. There are many opportunities. Processing tightly coupled with memory could be more interesting with some of these emerging technologies. More robust system designs can be enabled because of the non-volatility. And you can enable new applications because of the non-volatility and wide addressable access to persistent memory. But I'll talk about one thing that requires a different way of thinking about systems, going back to the future, as I mentioned earlier, merging of memory and storage. We've been designing systems that look like this for a long time. Basically, we have a two-level storage model, and that has evolved because volatile data is present in this main memory, and main memory is really fast. And we use a load-store interface to access that main memory, and that's heavily accelerated in hardware, so that we don't actually waste the latency and bandwidth provided by this main memory. But because this persistent storage was really slow, we use a different interface to go through and access it. Basically, we have the file system interface, and you have operating system and file system calls. And you manipulate the persistent data actually inside this main memory, so you do a lot of copies back and forth and do the translation. So this is maybe OK if your access time is milliseconds over here. But once you replace this with something like phase-change memory, which is very similar to DRAM over here, the code, the interface over here becomes a huge bottleneck. And I'll show you some results related to that. So what we would like to do is to unify the management as much as possible, such that we can eliminate all of that wasted work to locate, translate, and transfer data. And maybe even more, actually, if you can actually enable access to persistent data directly from the programming language, maybe you can do even more. And I believe this will improve energy and performance, and I'll give you some results. And this may simplify the programming model going forward. And this is the persistent memory manager. I'm going to skip this, but basically we want to expose a load store interface, manage data placement and movement, security, and a lot of other things. Once you're operating on data with a single interface, now you need to actually have metadata to identify the data. So this needs to be managed also. And this is a cartoonish picture of what we're trying to do. You have this persistent memory manager, load store accessible, and you have a heterogeneous array of devices. And basically, you can address all of them with a single address space. In fact, I think maybe it's more ambitious, but you would like to address every data in the world maybe with a single address space eventually. But I'm not sure if that's going to be doable. So let me give you very quickly what could be the benefits of this. This is from one application that's in this paper. It's storage bound. It's actually a postmark, which is a bad application, but that's OK. It's just a poster child for this. But there are a lot of other applications over here. Basically, it's storage bound. If you use hard disk drives, you waste a lot of time just accessing the hard disk. If you replace the hard disk with something like phase change memory and still have DRAM in the system, you get 24x performance improvement. Now, this still uses the two-level model. If you actually get rid of DRAM and have just phase change memory, which is slower than DRAM, and have a single level interface, you get 5x more. And we've gotten rid of DRAM in the system. If you add DRAM and do much more intelligent data management, you can actually do even more than this. So basically, we'd like to get this additional point. By the way, the things are not as dramatic because you have flash somewhere over here, which actually has a more smooth transition. But basically, there's a lot of performance left on the table because of the interface we have, because software becomes a bottleneck with these memories. And this is the energy improvements that you can get. So in the last
1 minute left.
Let me actually talk about how can we do better. I'm going to circle back and derive some principles. I've talked about a lot of ideas. I've left off a lot of ideas. But I think there are 3 cross-cutting principles in everything that I've described. And I think we're not exploiting that in the system today. And one is, if we want to scale memory, we definitely want better cooperation between the devices and the system. We want to expose more information to the upper layers, or figure out that information with the right interfaces in the system, like the different refresh rates, or different latencies that you want to employ for different parts of memory, which I didn't talk about, or different types of memories and their characteristics. And for this, we need flexible interface. For in-memory computation, we need flexible interfaces. And we want more information flowing from top to the down, like what we should do in memory, what data should be placed where. And we don't have these interfaces. The interface we have to memory today, including flash, is pretty bad. It's actually a very dumb interface that treats the memory as a storage device that does nothing intelligent. The second is, the next 2 will be very well known in the processor design domain, I think, better than worst case design. So memory has been ignored, perhaps. That's why we're not doing better than worst case design. But we're still optimizing lots of things for the worst case. Refresh rates, latencies, and other things also, reliability parameters. But worst case should not really determine the common case. We're leaving a lot of performance and energy on the table. And I didn't talk about this, but with the right interface, you can actually get rid of 30% of your DRAM read latency today, because DRAM latencies are dictated by the worst case operation today, 85 degrees Celsius worst case device. And the third is the heterogeneity in design. Again, this is very well known in processor design space. That's why we have the accelerators, right? But we're not doing this as much in memory. So heterogeneity enables a more efficient design, because there's no one-size-fits-all memory that's good at every metric. That can optimize what you want. So we would like to specialize and become asymmetric. Of course, clearly this adds more complexity, but for scaling, it's probably a good idea. And I believe these principles are coupled. If you want to actually exploit heterogeneity, you need better interfaces. If you want to do better worst case design, you need heterogeneity and better interfaces at the same time. OK, let me quickly summarize. Basically, I've talked about memory scaling problems. I believe these are a critical bottleneck for system performance, efficiency, and usability. In fact, it threatens system security, as I've described earlier. I've talked about new memory architectures. I think there's a lot of hope in fixing DRAM. Enabling emerging memory technologies. I talk about hybrid memory systems and single-level stores. I think there's a lot of hope there. And an orthogonal problem, regardless of whatever you use your memory, you devise your memory with, you need to solve the problem of quality of service if it's a shared resource across different workloads. And I've already given you the 3 principles: cooperation across the stack, better than worst case design, and heterogeneity. I'll acknowledge a lot of people whose effort actually went into this talk. I guess I'm the messenger here. But basically my students, my collaborators, and at different places. And funding, with the generous funding. Without that generous funding, we wouldn't have been able to talk about any of this or do any of this. And one thing I'll point is we have a lot of open source tools, so if you're interested, and we're going to put out even more. The Emulator tool actually does enable design space exploration for very different kinds of memory. It's a flexible DRAM simulator that models HBM, wide I/O, and different kinds of things. And we have different memory simulators at different granularities and an error model that we developed in collaboration with Facebook by examining their systems, actually all of their systems, and looking at the memory error occurrences in the entire Facebook server fleet. OK. Thank you. I'd be happy to take more questions.
So for years, we've had this very nice split between architecture and microarchitecture, where the programmer's view was the architecture, and the microarchitecture could do whatever it wanted to, as long as it didn't violate that contract. You seem to be violating that contract all over the place. What's the impact of that going to be?
OK, let me think about this. I think I'm not violating that contract. I'm just thinking about defining a different contract.
Well, you're making a lot of what's microarchitecture today, you're going to make architecture.
Exactly.
But that's really going to restrict the flexibility of the hardware design. We've made good advantage of that split.
That's right.
In hardware design.
I think that's where the interesting research challenge lies. How do you design an interface where you can still do the innovation without changing that interface all the time, and the software is written? And I think there are interfaces that are amenable to that. For example, if you have a packet-based interface to memory, I'm not advocating it, but I think if you have a packet-based interface to memory, the packets can remain the same, but then you can communicate different things within those packets, right? And you can, over time, adjust those packets somehow.
I agree, it's a research challenge.
Yeah, and how do you do it efficient, of course, becomes an issue also. But I'm not suggesting that you should break everything. Just design more clean interfaces such that innovation can happen independently still. But we can we can still scale. Yes?
What about another level of memory management so that intelligence such as the OS or system management software could change the mapping and do a copy to optimize based on the measured characteristics?
So, I mean, that makes sense depending on what that layer looks like. So you're thinking basically some software layer or hardware layer or some management?
I'm thinking memory management to switch between where things are stored. You may need to do movements from one to the other. But if you could get under the OS, similar to performance management tools, and then switch where something lies to optimize the actual execution performance.
I think that makes sense, actually. Another layer that actually manages your memory. It makes a lot of sense.
We tried that in scientific computing, and we ended up with a lot of data movement because different phases of the computation have different access patterns. Yes. So it's hard.
I agree. But I think with the 3D, if you have the computation capability in memory, maybe there is a different way of doing things. I don't know. Yeah, yes.
Would really take advantage of this sort of technology?
Which one? In memory computation or?
Anything. I can imagine that the inner loop of Google's search engine or something would say, oh yeah, here's a factor of 10.
So actually, that's what we did with the graph analytics research that I didn't describe as much. But basically, we've looked at PageRank computation, and that's very memory bound. And if you're doing that graph analytics over a huge graph, you can get 14x higher performance according to our results, and 10x reduction in system energy. So I think big graph analytics-like applications is one example, but I don't think it's limited to that graph analytics only.